Jai Hind friends, today we will discuss about the amplitude modulation. So we will start. First of all, we will start with the definition. What is the amplitude modulation? It is defined as the amplitude of the carrier wave is varied with respect to the modulated or message signal. So this message signal plays an important role here. With respect to this message signal, amplitude of the carrier is going to be changed. That we will discuss is in the next slides. So first of all, we should know about how many types of amplitude modulation. First one is a double sideband suppressed carrier modulation, single sideband modulation, and vestigial sideband modulation. That we will discuss in the future classes. So now we'll see the waveforms. Here, this is the message signal, as I told you, and the frequency belongs to the FM of the message signal. And here this is varying with respect to the time. Now next one is the carrier signal, and here this is varying with respect to the time, and here amplitude belongs to the AC and amplitude of the message belong to the AM. Carrier signal represented with FC, and FC is higher than FM because message signal are going to be imposed on the carrier. Basically, when we need to transmit the signal from source to the destination, what will happen? We will impose this message signal on the carrier signal. So with respect to modulation, or with respect to the imposition of the message signal on the carrier signal, this information will be propagating to the longer distance. Basically, is the longer distance. That's why this carrier signal is required, and that's why this frequency should be higher. Now this is the resultant of the amplitude modulated signal. Here this is the message signal, and here as per the definition, the amplitude of the carrier signal are going to be changed with respect to the message signal. You can see, you can observe from here this waveform. You can see and observe while seeing varying the amplitude of the carrier signal with respect to this message signal. Here this is the minimum amplitude. You can see, you can observe from here. Here is the maximum amplitude. Observe from here, and envelope of the modulated signal. Now this is the envelope of the modulated signal, this carrier plus message signal. So with the help of this message signal and the carrier signal, or message signal is going to be imposed on the carrier signal, we can generate the amplitude modulated signal. One more thing, we can feed the message signal and the carrier signal, as in by using some techniques we can generate the AM modulated signal. That means we can generate this type of the signal. So one technique is the square law modulator, and second technique is switching modulator. So we are using these two techniques in order to generate this type of the waveform. Now see, we are having FC. This is the message signal, as I told you, and this is the carrier signal, as I told you in the very beginning. So with the help of this message technique, with the help of this message and with the help of this carrier, what will happen? We will generate this signal, that is the amplitude modulated waveform. And here you will see this message signal. What is this AM? AM is the amplitude of the modulated signal, and what is the AC? AC is the amplitude of the carrier signal. What is FM? FM is the frequency of the message signal, and what is FC? Frequency of the carrier signal. So as I told you one thing, frequency of the message signal is lesser than frequency of the carrier signal. And second thing, as I told you, amplitude modulated wave, how we can generate the amplitude modulated wave while using scalar modulator and while using switching modulator. With the help of this message signal, with the help of this carrier signal, and while using these two modulation techniques, we can generate this type of the signal, and this is known as the amplitude modulated waveform. Now next part, when we'll rearrange the equation, as what I'm doing here, I'm taking AC as a common. When I take AC as a common, what I'll get? AM by AC, and remaining process is similar, and means remaining value is similar. You can write this value here, you can also write this value here. So what we are getting here, when we take AC as a common, 1 plus AM by AC cos 2 by FMT cos 2 by FCT. So AM by AC will be represented with mu. And what is mu? Mu belongs to a modulation index. either we can call this as the modulation index, or either we can call this as the modulation depth. So what is the role of this modulation index? Why this modulation index is important, that we will discuss is in the next few slides. Basically, first of all, we can write what is the modulation depth. That is the ratio of AM by AC. So mu belongs to the AM by AC. Now this is the another way to calculate the modulation index. First way, as I told you, how we can calculate, by taking this mu this AC as a common, and we will get this ratio. And second, what we are doing here, when you're talking about the maximum and the minimum amplitude of the modulated wave, so what we are getting, when we're talking about the maximum amplitude, we are getting this value. When we're talking about the minimum, we are getting this value. That means here we are having one cosine factor also. So when we're talking about this cosine factor, when we're talking about the maximum value, that cosine factor will provide us the +1. So here is the multiplication of the cosine factor. Then what will happen? Here we are getting the positive part. When you're talking about the minimum value, this cosine factor will provide us the, I'll write here with this minimum value. When we're talking about the minimum value, this cosine factor will provide us the negative part. So what we are getting here? Minus value. So cos, this is the equation 2 and this is the equation 3. So with the use of the equation 2, what we are getting, while we'll add both of the two equation number 2 and the equation number, you can see equation number 2 and the equation number 3, while we'll add this, what we are getting, ACAM, and here what we are getting, we're getting the equation in this way. That means the amplitude of the carrier, where we are talking about the amplitude of the carrier. Now we'll subtract the equation number 2 and 3. What we'll get, when we'll consider this part, that is the Amax value. When we'll consider this part, that is the Amin value. So what we are getting here, twice of Amax. So what we are getting, AM. That means amplitude of the message. So this is the amplitude of the carrier, and here this is the amplitude of the message. So this is equation number 4, this is equation number 5. When we are using this equation number 4 and equation number 5, what we are getting here, ratio of the equation number 4 and the equation number 5, what we are getting, AM by AC, amplitude of the message and amplitude of the carrier. So we can use this value, and while removing these two from numerator and the denominator, what we are getting, the modulation index or modulation depth is in this way, Amax minus Amin or Amax plus Amin. So either we can calculate the mu while using AM by AC, or either we can use as in this way. So we are having two value. And one more thing, either we can write mu will become equivalent to Ka AM. So what is the meaning of this Ka? Means this Ka belongs to here 1 by AC. So either we can write as in this way, either we can write as in this way. So now thing is that, what is Ka? Ka is the amplitude. What is this Ka? Ka is the amplitude sensitivity. This belongs to the amplitude sensitivity of AM modulator. So with respect to these three values, we can calculate the mu. Either we can calculate it in this way that I have discussed, while taking this AC as a common, and while considering maximum value and minimum value. So what we are getting, the result is in this way. That is this is the one part, this is the second part, and here this is the third part. This first and the third part will become equivalent, but only difference is that is somewhere we are getting Ka. So that part is also important for the numerical point of view, because somewhere value of this amplitude sensitivity is given to us, that Ka value is given to us, and with respect to this and AM value is given to us. So we can calculate the mu value while feeding the Ka value, amplitude sensitivity, and while feeding the AM value. So in the sum numerical we are getting AM and AC value, so we can directly calculate the mu. In the sum value we are getting the maximum and the minimum value, so we can calculate the value mu. Why this mu is important? That is one of the important part. So what we will get in order to fix the value of mu. So basically waveform or amplitude signal is largely dependent upon the this mu factor, yeah, this mu value, or we can call this as the modulation depth. Now see, first of all, when we are talking about the this waveform, you will see this is the message signal. This is a message or modulating signal, and here this is the carrier. The inner part is the carrier varying with respect to this message signal. Now see, this is the, here there is a no overlapping. When we are getting this part, when mu is less than 1, when mu is less than 1, then we are getting this type of the waveform, and that is known as the under modulated or under modulation. Either you write here under modulated or under modulation. So next part, when mu is equal to 1, then you will see here this is a message signal, and here this message signal is varying is in this way. Upper and the lower sideband is representing is in this way. Here you will see, here you can observe where no overlapping. So this is also known as the critical modulation. Now next one, when we are talking about the mu is greater than equal to 1. Now observe here, this message signal is varying is in this way. One of the side of this signal is varying in this way, and now we are talking about the second portion of the signal, that is varying is in this way. You can observe from here. Here you can see, here we are getting the overlapping. So that is the reason why this mu is important, why we are considering this mu should be as a modulation index should be a important part, because you can see when mu is less than 1 and mu is equivalent to 1, so that part should be a simple, that part should be simple or simplex part. We can retrieve this signal easily, but when we are talking about this, that is a complex part. So retrieving this signal is complicated, because you can see, you can observe from here, you can observe while seeing this, you can observe this value from here. So that's why mu should be important factor. So now next part, that is a bandwidth. This bandwidth is also very important part. So now you can observe when we need to calculate the bandwidth, that is the difference between the highest and the lowest frequency. That means that is the difference between the maximum and the minimum frequency. How we can calculate this? Now see, as you know that how we can get this equation using equation number 1, that is the standard equation of the AM. So what we are doing here, as you can observe here, we are having one cos values here and second cos values here. When we'll multiply this factor here and also multiply this factor with here, so while multiplying, what we are getting, one factor is this and second value is this. Now when we multiply here with 2 and when we divide here with 2, what we are getting, we are getting this formulation, and while applying this formulation, what we are getting, SC cos 2 pi FCT, that is as it is, and second portion is this and third portion is this. So these two portion, one portion, these two portion, this portion and this portion, we are getting this portion while using this formula. Now you can see we are having three frequencies now. When you observe this equation, we are having three frequency. One is this, second one is this, and third one is this. While taking these three frequency, we'll write the name of these three frequency. FC plus FM, this is the upper sideband. FC minus FM, that is the lower sideband, and carrier frequency, that belongs to the FC. So what we are doing here, when we are using this type of the frequency, means when we need to calculate the bandwidth, what we are doing here, Fmax will become equivalent to FC plus FM and Fmin will become equivalent to FC minus FM. So while solving these values, what we are getting here, in order to calculate the bandwidth, what we can write here, Fmax minus Fmin. So while solving Fmax minus Fmin, what we are getting, we'll feed these two values here, and what will be the bandwidth, that bandwidth of the AM signal will become equivalent to twice of FM signal. So while using maximum frequency and while using minimum frequency, what we will get? We will get the efficient value of the frequency, bandwidth of the AM, while fixing the value of FM, F max, and while fixing the value F min. Now see, this part is also very important. In order to understand the carrier, we are having three frequency that I told you. One is the FC, second one is the FC plus FM, and third one is the FC minus FM. This is the upper sideband and this is the lower sideband. While using these three frequency, we can understand the carrier. First of all, see what we are getting. Here is the message signal, and this message signal is varying with respect to the time. So now we are doing the Fourier transform. With the help of the Fourier transform, what we are getting? We are getting the message signal is in this way. Here we are using the carrier. This carrier is also varying with respect to the time as varying the message with respect to the time. Now using the Fourier transform, what we are getting? We are representing the carrier signal by changing the signal from the time domain to the frequency domain. We are getting is in this way. Now here this is the modulated signal or amplitude modulated waveform. Here this is the message signal, and here this is the carrier signal. Now you can see by doing the Fourier transform of this, what we are getting? We are getting this part. So as we know that this part belongs to your upper sideband and this part belongs to your lower sideband. Here this part belongs to your lower sideband and here this part belongs to your upper sideband. So here we are getting the carrier. So what is the basically drawback of the amplitude modulated signal? We are getting the additional carrier. We are getting the additional carrier that will create the problem. That I'll tell you is in the power when we'll study about the power. Now see, here is a message signal, here is a carrier signal, here is the amplitude modulated waveform. Here this message signal is represented is in the frequency domain. Here is the message signal, here is the carrier signal representation, and here is the amplitude modulated waveform. Why we are converting this thing is in the frequency domain? Because in order to understand the signal easily and efficiently, in order to calculate the value efficiently, in order to understand easily, so that's why for the ease of the mathematical calculation, we need to convert signal from the time domain to the frequency domain. Now see, this is the power relationship. When we're talking about the power, how we can calculate the power, and this power is very important. Here we will calculate, here we'll see what is the drawback of the amplitude modulated waveform. Now see, this is the one signal, this is the second signal, this is the third signal. As I told you in the previous slide, how we can calculate, how we can generate this type of the signal. Now see one thing, when you're talking about this is the FC signal, and here is in this part, I'm considering this is the first part, this is the second part, and this is the third part. In the first part, there is no message signal existing. So this is the totally wastage. This is the wastage of power. Why we are calling this the wastage of power? Because here there is no message signal. Here this is the upper sideband, and here this is the lower sideband. Now when you see power of the AM wave is equal to the sum of the power of the carrier upper sideband and the lower sideband. That means this sum of the power, sum of this carrier. I am representing here, this is the carrier power, this is the upper sideband power, this is the lower sideband power, and here this is totally wastage of the power, because as in this part there is no message signal existing. So now we will understand this. Basically when we're talking about the like your power of the DC signal, and while using the cosine signal, we can calculate, we are using this formulation. So what is the value of the VRMS? That is Vm by root 2 whole square by R. So this is the result of the PAC waveform. It is a PAC waveform, the result of the PAC waveform by using the cosine signal. VRMS is the RMS value of the cos, and Vm is the peak value of the cos signal. Now first of all, we'll calculate this PC. How we can calculate this PC? PC is equal to Vm by 2 into 1 by R while using this part. This is the journal. This is the journal result. This is the journal result. And here I am using this journal result in order to calculate this PC. So now first of all, what is the value of VM? VM is the maximum peak. You can see here, peak value of the cause signal. Here is the peak value of the cause signal, that is AC part. So I'll write here AC to R. So that part belongs to your PC. That means when we are talking about the power of this carrier, that is AC into AC by 2R. Now we are talking about the power of the upper sideband, power of the lower sideband. So when we need to calculate the power of the upper sideband, power of the lower sideband, and this is your general expression, while using this, we need to first of all calculate this VM value. So how much is this VM value? This VM value is a maximum value, and here this maximum value is the AC mu by 2 for the upper sideband. You can see here, and AC mu by 2 for the lower sideband. Now I am talking about this upper sideband. How we can calculate this upper sideband? As we know that VM by, when we're talking about the general expression that I have told you, so VM by root 2, I'll write here this PC or VRMS by R, that is VM by root 2 whole square by R. Yeah, you can also write 1 by R. So how much is the value of VM? You can see from here, this value of VM is this for the upper sideband, this for the lower sideband, similar value. So we'll write here, when we feed here, when we feed here this VM, what will get? ACAM, yeah, I'll write here AC mu root 2 whole square. You can see here AC mu by 2, AC mu by 2 root 2, yeah, is in this way. I'll write AC mu by 2 up into root 2 whole square into 1 by R. So how much you'll get? AC square mu square 2 to 4, and here this 2, and here 1 by R. So what we'll get? We'll get this part only. So now lower sideband, upper sideband you have calculated. Now we need to calculate the lower sideband, and thing is that in the lower sideband, similar result we are getting, similar result we are getting is in this way. VM will become equivalent to AC mu by 2. So we'll feed this value is in the standard result, and with the help of this value we can calculate the lower sideband is in this way. Now we will add all the three powers. What we are getting the result is in this way, that is in this way. This is the power of the carrier, this is the power of the upper sideband, this is the power of the lower sideband. Now as I told you, when we are talking about the power of the carrier, you can observe here this first part. This first part is nothing but the wastage of the power. How this is the wastage of the power, that I'll explain you, that I'll tell you in the next slide. Now see, basically what we are getting, first of all we need to calculate the power of the sideband. That will become equivalent to the power of the upper sideband plus power of the lower sideband. So sideband means combination of the upper sideband and the combination of the lower sideband. So how much is the upper sideband? That I have told you, that is AC square mu square by 8R, here AC square mu square by 8R. When you calculate this, what will get? AC square mu square by 4R, that is the power of the sideband. So this is the one result. Now power of the sideband is equivalent to, I'll reshuffle this equation, that is AC by 2R and mu square by 2. So when we'll sort out this, as you know that what is this, that is the power of the carrier mu square by 2. So you'll get that this power of the sideband is in the term of the power of the carrier, here this is the power of the carrier, here this is the power of the sideband. So now, as we know that the total power, when we are talking about the total power, PT will become equivalent to PC plus P sideband. PC means power of the carrier. So when I'll take mu is equal to 0, so this PT will become equivalent to PC, because when I write this sideband power, that is PC mu square by 2, and here this part will become equivalent to the 0, so this complete set is 0. So what we'll get, PC is equal to PT, total power will become equivalent to the carrier power, because when we are talking about the carrier power, this is the carrier power, here no mu, when we are talking about the carrier power. So now we are considering second case, when mu is equivalent to 1. So when mu is equivalent to 1, so total power will become equivalent to the carrier power plus carrier power mu square by 2. So what we are getting here, when we will feed this type of the result, what we are getting, that total power will become equivalent to this mu is equivalent to 1. So what will get, PC plus PC by 2. So when we will solve this, what will get, we'll get here 2 by 3 of PC. So carrier power will become equivalent to total power, one second, here this is a 3 by 2, so total power will be, this carrier power will become equivalent to the total power by 2 by 3. So when we solve this, what will get, PT into when we solve this, we are getting here, okay, we can see from here only. So in the final, what we are getting, this power, carrier power will become equivalent to the total power into 2 by 3. So what is the meaning of this? When we'll need to convert these values in the percentage, what we'll get, PC will become equivalent to 66.6% of the PT. That means when we're talking about the total transmitted power, so 66.6% of the power is going to be waste when we're talking about the carrier power. So that is the major drawback of the this amplitude modulated wave. Is a drawback. The drawback of the amplitude modulated wave, because 66.6% of the total power is going to be waste when we're talking about the carrier power, and when mu will become equivalent to the 1. So that's why we are calling amplitude modulation, when you're talking about the amplitude modulation, the power is going to be, lot of power is going to be waste because of this carrier, as I told you, because of this carrier, because of that portion of the carrier. 66 point you can see here 66.6% of the carrier is wasted when we are talking about the transmission of the amplitude modulated wave. But why we are using then amplitude modulated wave? Because a lot of the power is going to be, unnecessary power is wasted, but demodulation is easy. Its demodulation is easy, and there are n other advantages. AM is economic as well as easily obtainable. AM is simple to implement. That's why we are using AM. Instead of that, this power is going to be waste, but there are n other advantage and disadvantage that we will discuss in the end of this this complete course. After means this end of this modulation and demodulation, then I will tell you some advantage and disadvantage. Here only we can understand why we are using this, because of the advantages at the demodulator side, and that is the economical, that is the one. AM is the economical and easy to implement, or simple to implement. That's why we are using this amplitude modulation. So hope you are getting. Next, in the next lecture, we will discuss about the generation and how we can generate the amplitude modulation.